Okay? So now we're going to try to make a little bit more sense about everything we've been doing with respect to the stress tensor and principal directions and other things. Start to put it into some context of what we can do with it if we understand these things correctly. And one of the things we can do is we can resolve the stress on a fault at depth in the earth. And the reason that's important is because the ratio of the normal stress to the shear stress on a fault and its coefficient of friction is what determines whether the fault's going to slip or not, right? And so just to introduce some terminology, we have we'll typically use a coordinate system that's now oriented with respect to the directions that were, the cardinal directions, north, east, west, south, right? And the typical it's a right-handed coordinate system, and you'll see it on the next slide, but it's a right-handed coordinate system such that you take north, east, down. Okay, so everybody remember what I mean by right-handed, right? So you take your right hand and you put it in the direction of, say, the north. So you'd point your fingers north and you curl it to the east. You curl your hand to the east, and the direction your thumb is pointing gives you the other positive. That's what gives you positive directions, right? So if it's right-handed, you go from north to east, and your thumb is pointing down. That means down is positive, right? Everybody remember that from statics? And so when we talk about the strike direction of a fault, so this is a representative of fault plane. When we talk about the strike direction, in this case, as it's drawn here, it's perfectly oriented north. Okay, so in the next slide you'll see an angle that defines it, or later you'll see an angle that defines it with respect to north. Okay, and then the dip is the angle. Well, I don't know that I need to just redraw these angles, but the dip is then this angle, and the rake is the angle with respect to the vector of slip. So let me see if I can draw this. So if we have a fault, so if we have a fault like this, right? So this is the hanging wall. So we're just talking about a normal fault, where this is the hanging wall, and this is the foot wall. The direction of slip, well, in this case, it doesn't have to be straight down. It could be slipping, say, for instance, in a direction that's like this, where this arrow is in the plane of this fault, right? So then the rake would be the angle between the slip direction and south. And so it'd be this angle. So if the foot wall is moving at an angle, right? Does everybody understand that? I see a lot of shake your head. Yes, I understand.
Can you push down and
Yeah, it's not move. Think of I said normal fault. Think of a strike-slip fault, right? I know we've defined strike-slip faults that where the motion is just like this, right? But we know it's never that simple, right? The motion is never going to be perfectly planar. Do what? I don't even know what that is. Okay. Okay. All right. So let's think about a strike-slip fault, right? So the way we typically talked about them is that the motion of the fault is just perfectly shear, okay? But in reality, that's not. It doesn't always move perfectly right to left or whatever, right? There's always some up-down motion, right? So that up-down motion, the angle of the slip, right? So that the up-down motion defines, if I drew a vector that traced the motion of this hand on this hand, right? That would be the slip direction. And the angle between that vector and our geographical coordinate system, in this case south, would be this rake. All right. I'll try to come up with a better visualization, maybe for next time. And so what we're going to do is we're going to use these tensor transformations that we talked about before. We talked about them before in the context of eigenvectors, but we're going to use the way that tensors transform to take our principal directions and put them into a geographical coordinate system. Okay? So now here we have our NED coordinate system, right? And this time I have it drawn properly. So it's north, east, and down, okay? And also have some arbitrary set of principal stresses and directions drawn there, okay? So depending on the faulting regime, I mean, most of the time, like we've been talking about, if S3, if S3 is if either S3 or S1 for normal faulting would be the vertical stress, and they would be in the direction of D, right? So it would be rotated such that this vector is pointed straight down along with it, okay? But otherwise, we have, for an arbitrary set of principal directions, and remember these are orthogonal, right? They're all 90, even though it's maybe a little bit difficult to see in the way I drew it there. They're all 90 degrees to one another, okay? And so for an arbitrary set of principal directions with respect to our geographical coordinate system, which aligns with north, east, and down, then we can define these angles, okay? And we'll use those angles to then transform whatever the principal directions are into the geographical coordinate system. And then once we have that, we can use that to then transform it again onto the fault plane to determine what the normal and shear stresses are on a fault. And then that gives us some information about whether the fault is likely to slip. Okay? So if you remember, I've written this equation before. It just looked a little different. Before, we had something like S prime equals QT SQ, okay? So in that scenario, it's the same idea. These Q's are transformation matrices, the same as this R is. So the idea is that in the case we looked at before, this was an arbitrary stress, and we wanted to transform it into the principal stress directions. Okay. Now, now we have a stress S that's already our principal stresses, so that's S1, S2, S3, and we want to transform it into SG, which is this geographical, the stress associated with the geographical coordinate system, okay? And so we'll use these rotation matrices or transformation matrices to do that. And so with these angles defined as they are, then we have this is our transformation matrix. So what that will do is transform any arbitrary principal directions into our geographical coordinate system. All right, so I know it's kind of messy, but all you have to do is know what those angles are and plug them in, and then you have a matrix. Right? And then you can use that matrix. You can use your matrix multiplication that we learned to do the transformation. Okay? All right, so let's work an example. Does anybody have their calculator out? All right, so just real quickly, let's do this one time. Somebody has their calculator out. Remember that alpha is 0, beta is 0, and gamma is 90, okay? Plug it in there. Plug in alpha, beta, and gamma. What's the cosine of 0? So you're going to have 1, 1. So 1 times 1, that's going to be equal to 1. Right? What's the sine of 0? 0. Sine of 0 is 0. Over here, I see some sines of alpha and betas in both terms, so that's going to be 0. Same here. Well, this is going to be 0, and then you have cosine alpha, which is 0, cosine of 0, which is 1, and then cosine of gamma. What did I say gamma was? 90. What's the cosine of 90? Are you sure? I may have, yeah, what's going on here? Let's see. Oh, yeah. I was looking at something different. Okay. So then, I wonder if I made a typo. Do what? No, this should be a 1 here. So let me double check my. I'll have to double check this equation. Obviously, you're going to have to use this on the exam, so it needs to be right. It needs to be right. Let me. I may have made a typo here. Let me check this in my notes. I'll get. But yeah, you can use it. All right, so anyway, what I was after was an RG that reduces to 1, 0, 0, 0, 1, I'm sorry, 0, 1, 0, minus 1, 0. All right, and so then what's RG transpose. When you take a transpose, what do? You take the rows and the columns and you flip them, right? So the first column is going to be the first row, so that's 1, 0, 0. The second column is going to be the second row, so 0, 0, minus 1. And the third column is going to be the third row, 0, 1, 0. All right. So I usually do this in 2 steps. So, I mean, ultimately what we want is SG is equal to R transpose SR, right? So let's do this part first, the SR. So SR is 30, 0, 0, 0, 25, 0, 0, 0, 20, 1, 0, 0, 0, 0, 1. Okay, so who remembers how to do matrix multiplication, right? What is this first term up here? It's in words. Like, how would you do it? Yeah, how about we take the dot product, right? Take the dot product of the first column here. First column, I'll call this B, and this A. Well, no, let's call it S and R, right? Okay, so the first column of R times dot product, first row of S. So you got what? For the first term. Okay. And then second column of R, dot product, first row of S. 0. Third column of R, dot product, first row of S. All right, now the second. So first column, second row. First column, dot product, second row. Second column, second row. Third column, second row. First column, third row. Second column, third row. Third column, third row. All right, so that's SR, and then I want to multiply this, so now this is SR. I want to multiply that by RT. Right, so then I have 1, 0, 0, 0, 0, minus 1, 0, 1, 0. And so I'll just write down the answer. It's 30, 20, 25. So this is SG. All right. So we have our 3 principal directions and principal stress. Right? And we rotate that into our geographical directions. And so that's the stress associated with the coordinate system, our geographical coordinate system. That's the stress tensor associated with our geographic coordinate system.
Yeah,
Okay? Yeah.
just
Yeah, this is a transformation matrix, so the inverse is the transpose. Yeah. Well, so the transpose is its inverse, so you don't have to do. Yeah, and it doesn't matter what any value of alpha, beta, and gamma that you plug into that matrix, you'll you'll always have a unitary matrix. So that's that's the answer that we just worked out. I have other examples from other faulting regimes. So I don't know, somehow my little fragment fly-in's not working properly. I have to fix that. But so I actually encourage you. I mean, you're going to have to do this on the test, so I encourage you to get some practice. I'll also probably give you a homework assignment associated with this today. So anyway, the point is, I've given you a couple examples here from different faulting regimes and the answers. So you can go and you can work through these examples. I'm not going to just work through all of these in class, but because it's just more of the same, right? It's just more of the same. I give you S, I give you RG, you compute SG from RG transpose times S times R. Right? And I give you the angles. Okay. So